For lesson 15, functions involving percent change. Your warm-up question, all books at a bookstore are 25% off. Priya bought a book originally priced at $32. The cashier applied the store-wide discount and then took another 25% off for a coupon that Priya dropped. If there was no sales tax, how much did Priya pay for the book? I'll give you another minute. Maybe if your whole group is done, you can talk it out. I'll start asking people shortly. But table 8, what did you get for your answer? How much did she pay for the book? Some numbers on your paper. What do you think? How much did you pay for the book? Dot. Come on, guys. I don't expect you to be like 100% accurate during the note taking. Table 8.
$16.
Okay. Did anyone get an answer other than 16? Bella, what'd you get? 18? Any other answers out there? Okay. Other answers? Anything else? I do expect a variety of answers, even though I did say, like, I've taught you enough that I think you should be able to answer this, right? But there are common mistakes that students make, so that's why I am kind of expecting a variety of answers. Table 1. Okay. What? Okay. So anytime you answer a word problem, always go back, see that your answer makes sense. So if she is buying a book that was originally $32 and it's on sale and she has a coupon, should our answer be over or under 32? So one of these answers can definitely never work. But okay, we still have a variety of answers, so we need to see. First, let's consider, and there's lots of ways you can do it. We are applying the store-wide discount of 25% off. How can I figure out what 25% off of 32 is? Okay. If I divide by 0.25, the number will get bigger. Okay. Multiply by 0.25. I think some people could have like divided it by 4, because quarters, like there's 4 of them in a whole, but it's probably easier to multiply it by the decimal of the percent. So 25% is equivalent to 0.25. What is 25% of 32? I'll just guess. 8. That's the first discount. That's the store discount. That's not what she's paying. That's just the store discount. To get what she's paying after just that is how much does she pay just after the store discount? But then she has a coupon that gives her another 25% off. Listen. You cannot just combine 25% plus 25% and say that it's 50% off. It doesn't work that way. So those of you that said 16, a lot of you said it. It doesn't work that way. You have to then see the price it's at now after the discount and now apply the coupon, which happens to be another 25% off. So we're going to times that by 0.25 What is 25% of 24?
6.
6 is 25% of 24. So that's my coupon discount. And in order to get what she's actually paying, you take the 24 minus your coupon, which makes the real price now. Okay. So that's the real answer, and that's how you get it. So don't make that mistake, just combining the percentages. You have to apply it each time, if that makes sense. Now, some of you may have picked up on an easier way to do it, which is what we're trying to push you to because it's exponential functions. All right. Yesterday, we really looked at when exponential functions, when it's better to use this formula instead of the other one we've been using. When is it better to use this formula that I'm highlighting?
When it's
Anyone? Okay, stuff can increase or decrease in this one too. But specifically when it's increasing or decreasing by a. Yeah, I know you guys like want to say it, but you're still so shy. What was that, Haley? By a percent. So when it's a percentage increase or decrease, probably use this one. Where instead of B, they replaced it with the 1 plus or minus R. Where R is your growth rate as a decimal. So in this one, what was our original amount? Table 1, what was our original amount? 32. So A is still for initial amount. Would the discounts be adding or taking away from the price? So I would do the 1 minus, so it should be decreasing. And what was the rate as a decimal? 0.25. And then the exponent, or the x, would be how many times are you applying that change? In this example, how many times did we apply the 25% off? Twice. So if you do this in your calculator, you will get the same answer that we got. I know sometimes it's hard to like, I don't know, problem solve your way through it, but it is possible, like how we did over here. But if you recognize that you can use this method, then maybe that'll make your life a bit easier. Okay. So there's that. When it's a percentage, maybe consider using this. On your test though, also be able to recognize that they might write the expression like this. Where they already did the subtraction or addition. So timesing by what remained, if you did that earlier, good for you. As long as you get the right answer at the end of the day, that's all I'll see, is the right answer. So questions? All right, so again, in my opinion, this is all just practice. We've done it before. But by the end of the lesson, we'll use graphing technology to compare the different percent increases or decreases. And also just more practice writing the expressions when we're applying a percent repeatedly. I'm recording right now, just like I do every day. The highlighted link is always this day's lesson. The other links are from last year in case anyone works ahead for the puzzle piece is lesson 15. And you do have a quiz tomorrow. Quizzes I'm not super worried about. I mean, some of you can see that at the beginning of the semester, your quizzes can really bring you down a lot because there's nothing else in there. Next week, we take our unit tests. That's when 150 assessment points will be added to the mix. So you really want to make sure that unit test is the really, really good one. Okay, boys, stop. You want to make sure that unit test, the 150 points that are going in, are way better than what you've been producing. Use the quizzes, use the practices as practice. I also have one of the study guides published already. I'll show you that in a second. But the unit test is like what really kind of makes or breaks you. It's gonna be more of your grade than the other stuff. Plus, if you score higher on your unit test than you did on your quizzes, I do match the score. So say you've been failing all your quizzes, but you managed to get a 65% on the test. I'll make your quizzes 65%. Say you failed all the quizzes, but managed to get 100% on the test. I'll make your quizzes 100%. So keep that in mind. But yeah, if you're failing right now, expect an invite to Saturday Academy from me. Or just come to tutoring in general. If you can't come Wednesdays, the other algebra teachers are available on the other days. So like there's no excuse. But if you look at Schoology, this is more for my overachievers or just people that really, really need to get their grade up. I already have one of the study guides published. I put them right at the top so that you don't miss them. I will pass out the paper copy probably Monday next week. But you're welcome to look at it, do it on your own paper. And this is what your constructed response test will look like. So, different numbers and different graphs maybe. Questions on anything I just said? It doesn't want me to scroll, but it's in there if you want to take a look. All right, so some practice activities, owing interest. To get a new computer, a recent college graduate obtains a loan of $450. She agrees to pay 18% annual interest, which will apply to any money she owes. She makes no payments during the first year. Really, you could answer all four of those questions, but we'll just start chunking the first two. How much will she owe at the end of 1 year? And then if she continues to make no payments, how much will she owe at the end of 2 years? And then 3 years. If you get stuck, refer back to that equation I talked about in the warm up. Or ask me for help, but I'll give you 3 minutes before we review these questions. Okay, so table 9, how much will she owe at the end of 1 year? $81. Now, does that include the $450?
I'm not sure I did the first.
Okay, well, the amount she owes should include the $450 as well. So like not just the interest, is the 81 just the interest?
Oh, yeah.
Okay, so let's see if that would be true, and you could have solved this a number of different ways, but I'll show you how to get the equation to match our exponential functions. So if she has $450 and it charges 18% annual interest, what does annual mean?
Yearly.
Yearly. So if you didn't know that, I meant to tell you earlier, I just forgot. Annual means yearly. Biannual means 2 times a year, and so forth. But if it's 18% interest after 1 year, what is 18% of $450? How can I calculate that? Times it by 0.18. And then is that where we got the 81? Cohen?
Yeah.
Okay, so that is the interest, but keep in mind, they now owe the interest plus the original amount. They didn't pay any of it back.
Yeah, I just forgot that.
Not a problem. So that's why I say like go back, read it. Sometimes it asks for the interest. This one's asking for the total. So add it together and it should be
531.
wait good. So everyone else adjust. There is a way to make it not 2 steps. And that's by applying your kind of like your exponential function way of doing it. If I use this equation that works for applying percent changes. A would be my initial amount, 450. I could do 1 plus my rate as a decimal, and I'm doing plus because interest would add to the total. And this is just after 1 year. So my exponent would be 1. And then when I put this in my calculator, I also get 531. In case you don't believe. So 450 times 1.18 also gives you that same amount, which is our real answer. So then at the end of 2 years, table 2. At the end of 2 years, do you have the total? Or can you tell me, is there gonna be a different initial amount? So initial amount still the same. Is the interest rate any different at all? So it's still gonna be times 1.18. But since it's 2 years, we can change that exponent to a 2. That's one way to get the answer. Another way could be, well, here's my new starting amount, 531. Times it by the 1.18 just 1 time. And that'll give you the same answer for after 2 years. But I would just recommend, keep it simple, keep it like this. Just change the exponent for however many times the 18% was applied. So then when we put this in the calculator, table 2, what do we get? All right, that's how much she owes at the end of 2 years. And I think it was already 2 decimal spots, but if it wasn't, we're talking about money, how much she owes, so just make it look like that. Sometimes on your test, it'll be specific to what it wants you to round to, but yeah. Table 3. After 3 years, how much does she owe? Okay, that sounds familiar from when I did it earlier. I'll double check in a second. But the only thing that should be different in your expression is what? The exponent. The only thing that's changing each time is the time frame, right? So that's it. If we put this in the calculator, then this is the right answer. Good, questions on that? All right, so now add in the other 2 questions, the 3 and 4, which are still about the same situation. I'll come back to this, but I'll read you 3 and 4. So to find the amount owed at the end of the 3rd year, which we already calculated, a student started by writing the following and ended with writing 450 times 1.18 times 1.18 times 1.18. Does her final expression correctly reflect the amount owed at the end of the 3rd year? Then write an expression for the amount she owes at the end of X years without fee. So don't overthink it, just add those 2. I'll go back to these ones as a reference. So does her final expression correctly reflect the amount owed?
Yes.
And why can we write it like this also?
Because it's just rewriting it.
Okay, so if we wrote it with an exponent of 3, it would condense that. All right, exponents tell you to multiply the base by itself that many times, and this is our initial amount. So like they did the year 3 amount, which was 739.36 initially. they did the year two amount, which was, I'm forgetting, 626.58, thank you. And then they added that again, I'm not really sure why. And then they also times it by 0.18. Oh yeah, because they were figuring out what 18% interest of that was, adding it to this to now figure out their total. I think you guys get the point.
Yeah.
It's much easier to do this, you just have to remember your setup. Now, this next question always throws students off. Why, I don't know. It's like you get it when it's numbers involved, but then once we throw in a variable, we get confused. So then table 5, do you have an answer for that one? Okay, what do you get? Okay, perfect. That's it. So this can solve for any amount of years. 2.5 years, 100 years, 10 years, whatever it wants X to be, it varies. That's why we're using a variable. Everything else stays the same. Initial amount stays the same, the rate it's changing stays the same, it's still growth. And there's no payments involved. That's why it's staying. So good, any questions? All right, the next part. Just a little more practice. New situation. So suppose three people each have taken loans of $1,000, but they each pay different annual interest. So annual means what again?
Every year.
Yearly is when it's being applied. Now, for each loan, you're gonna write an expression using only multiplication. So make it look like your exponential functions for the amount owed at the end of each year if no payments are made. Also, we want an expression. We don't want like an answer necessarily. We want a setup. What you'll do after you set it up is you're gonna graph them all using graphing technology to remember to adjust your window how I showed you. And then see how many years would it take for the original unpaid balance of each loan to double. Okay, so do that. I'll give you, I don't know, 5 minutes. Everyone needs to practice the graphing. Everyone. Yes. That was a good question that Brooklyn asked. So if you didn't hear it, here's that question. We're having some confusion on when to use this equation versus the one with the 1 in it. So when is it better to use the first one? They both represent exponential functions. When is it better to use a times b to the x? They say phrases like okay. Can you tell me what's different between the two? Tell me what's the same between the two. Asking the whole class. Tell me anything about what I wrote down. Anything at all. What's the same? What's different? 9. Okay. So the exponent is the same in both. What else is the same in both? The a. What else is the same in both? The y. So then that leads me to the question I originally asked. What's different? The parentheses and the b. So you use the first one, when it's just a b, when it says things in the problem like what? What's different from these lessons to the previous one. I'm gonna use the one with the R in it. What does the R stand for? Okay, so it's your rate as a decimal, which you get from a percent usually. So you'll want to use the second equation when there's percent changes involved. So increasing or decreasing by a percent like it has been lately. This other one you would use when it says things like it's doubling each time. Because then B is just 2. Or like it's tripling each time, then B is just 3. It's halving each time, then B is 1/2. Or like if you know what the common factor is, like if you see a table and you can tell what it's multiplying by each time to get the next one. Does that make sense? That's what we've seen all prior to yesterday's lesson. Now, if there's a percentage involved, it's less easy to see that we're timesing by 1.18 each time. So that's why we use this setup. Both mean the same thing. Like if it's doubling, it'd be 1 + 1, because it's literally doubling, and it still becomes 2. But this one's better for our percentages. Does that make sense? Okay. So now continue with the rest. Make your equation using the exponential function setup. Graph each one. And be able to answer number 3. How many years would it take for the original balance to double? Right? Time starting now. Okay, look to the screen, confirm your answers. So I saw some that just had like numbers, like, I don't know, they got 1,000 something for their answer. It wants to know for each year, like it didn't specify a certain year. So for each year, you would put an X for the exponent, because that's what would change depending on what year you're trying to find. So just the expression is what you needed. So they all have the same initial amount. They all started at $1,000. They all have different rates. So does interest add or subtract to the total? It adds. So you should expect, like, if you take out a loan with interest, that you're going to pay back more than like the original amount. That's why all of these B values, because this is still technically B when it's attached to the X, those are all growing. They're all bigger than 1. Now, the decimal you get from dividing each percent by 100 if you're not sure. So even that 30.6%, you're not sure, divided by 100, it'll give you the accurate decimal, which then you add to the 1 per the formula. Make sense? Okay. So it's decreasing by that much, we do the 1 minus, but interest adds to the total you owe. So would higher interest be better or lower interest be better? Lower interest, the lower the better. So the next step, hopefully you got to it, was to use graphing technology so that you can answer things like number 3. So once you make the expressions, you should be able to graph them all in the same graph so that you can compare them. Okay. Then, so I don't see anything right now, so I have to like play around with the window. What I do see is not that helpful. So I'll show you how to adjust the window, but it wants to know when each loan will double the original amount. So what would double of 1,000 be? 2,000. They want to know when each loan doubles. So when it reaches 2,000. And since you have it graphed, you can see exactly when it reaches it. But the way my graph looks right now, I'm not seeing much. So here's how you adjust the window. Press this little wrench. Our X's, like we don't need any negative X's. We're not going to look at any negative years today. And I don't know how long it'll take. So I'll just guess like 10 maybe and then adjust from there. We want to know when it reaches 2,000. So have your y-axis like be maybe a bit over 2,000. Your y-axis could start at 0 if you want it to. And you could hold down until you see that it's 2,000 exactly. Another thing you can do, I know the equation y equals 2,000 will give me a line here. And then it makes it really nice. Desmos lets you click where they intersect. And you could see exactly when it reaches 2,000 for each one. So for this green line, that goes with which loan? Loan A, B, or C? We know how to read the expression? The one that I already showed you, maybe you should have written it down. So which one does the green line go with? Loan C. Loan C grows the fastest. It reaches the $2,000 mark first. How long does it take to reach that mark? Read it. About 2.6 years if we're rounding. So for loan C, it takes 2.6 years. You guys now, and I did kind of accidentally show you the answers earlier. I'm not sure if anyone wrote it down though. You guys now using your graphing technology, see when exactly it reaches $2,000 for the other loans. But practice using your graphing. Need for help if you weren't listening. Table 7, can you tell me which loan grows the slowest? Loan A. You can see it's the red line on my graph. It takes how long, class, for it to reach $2,000? About 6.1 years. So loan A, and this should be going on your notes. It takes 6.1 years to reach double the amount. Then table 8, for loan B, how long does it take? You out with showing you what things that is, now you just gotta interpret it. So how long does it take for loan B to reach 2,000? 3.2 years. Okay, good. Any questions? All right, I could do the last example, but we won't. I'll give you time to work on your practice instead. But know that average rate of change will be on your quiz tomorrow. That lesson seemed to go pretty well, but that was like last week. Make sure you review all of lesson 8 through 15 for your quiz tomorrow. But all your notes are up to date. I'm ending it here so that you can work on your practice, not so you can just like sit around and wait for yourself.